Black holes are one of the most mind-boggling aspects of space. For a start, they aren't actually objects. They are the result of the extreme warping of space-time. And because of this warping, some really weird stuff starts to go on around them that will change your perspective of the way the universe operates around you. Some of it is so strange that perhaps you won't believe it was true were it not for the solid math that back up their existence and properties, and the increasing evidence that the math is correct through observations in our own universe.
I'm Alex McColgan and you're watching Astrum, and in this video we will be exploring the unexplorable. Join me on this journey as we attempt to understand the weird science of how a black hole forms, what goes on around them, and explore what might actually allow for an escape from the most inescapable prisons in existence. I hope by the end of this video to have earned your like and subscription.
Black holes come in a variety of sizes. The smallest observed black hole is around 3.8 solar masses. On the other side of the scale, we find black holes that have been in existence since almost the start of the universe, black holes weighing billions of solar masses. These behemoths are not only massive, but also huge. They would easily fit in the entire solar system within the diameter of their event horizon. Black holes being created today are the final stage in the life cycles of particularly massive stars. When such a star is born, it is essentially balancing under the weight of two forces. The first is gravity, pushing its mass towards its center. Down in the depths of the star, hydrogen atoms are crushed against other hydrogen atoms with such force that they combine to form a denser element, helium. This new atomic structure actually needs less energy than it did when it was two individual, separate hydrogen atoms, so the extra energy left over gets released. This released energy is the second force. It radiates back out from the center of the star as heat and light, counteracting the force of gravity pushing in. In this state, the star will remain relatively stable until such a time as the reaction begins to stop as it runs out of its hydrogen fuel. If the star is massive enough, once the hydrogen begins to run low, the star will combine the newly formed helium into even denser materials like carbon, neon, and eventually oxygen and silicon. But then it begins fusing iron. The issue with iron is that it doesn't save any energy in its new form, so has no spare energy to release. It just sits in the core of the star, growing larger. With no energy pushing back against gravity, very quickly the scale tips. The energy of this collapse is astounding, but the force is dependent on the original mass of the star. Like a hammer striking on an anvil, the mass of the star rushes down to meet the core with such force that the rebound of that blow is what we call a supernova. Matter and energy are blasted out across the universe from the crackback in one of the largest explosions possible, which produces elements even heavier than iron, all the way up to uranium. And what is left of the star? Well, it depends. If the mass of the star, and thus the force of the blow, was too low, what remains is a neutron star, a small ball of matter at most around 25 kilometers in diameter, and yet so densely packed with mass that it equals 1,000,000 Earths. But if the mass, and thus force, was big enough, physics as we know it breaks down, and we are left with a black hole. When you see an image of a black hole, the black sphere you are looking at is not actually the black hole itself. Scientists theorize a black hole's true form is probably even smaller and denser than a neutron star. In fact, it is likely infinitely small and infinitely dense, a singularity emitting forces that warp time and space itself. However, we don't know, and the reason we don't know is because of something called the event horizon. All objects with mass exert gravity. We've known this since the days of Newton. However, when Einstein came along in 1915 with his theory of general relativity, a contemporary of his called Karl Schwarzschild reasoned from it that there could exist objects that were so massive they could create enough gravity that light itself could not escape. And if even massless light photons couldn't get out, nothing could. When you look at a picture of a black hole, you are not seeing the black hole itself. You are seeing the event horizon around it, the demarcation line where gravity has become so powerful that light can no longer leave. There is nothing but darkness. Now, its effect on space is one thing, but black holes also impact another aspect of the universe, time itself. You see, according to Einstein, space and time are inseparably connected, and mass warps space-time. With the singularity's infinite point of mass, it stretches space-time so much that the event horizon also marks the point where time stops. Within the event horizon, space and time basically cease to exist, a place where there is no where or when. This produces an interesting phenomenon to an outside observer watching matter fall into a black hole. From their perspective, as matter approaches the black hole, it will slow down until just before the event horizon, where it will stop altogether. You won't ever see it cross the event horizon. There will be no satisfying absorption. Instead, the matter will gradually dim until you can't see it anymore. When first theorized, astronomers and physicists were uncertain if black holes were actually real. It was only 40 years later that the first evidence of a black hole was recorded. In 1964, using newly developed X-ray satellites, scientists noticed an object in the constellation Cygnus that seemed to be emitting a large amount of X-rays. Strangely enough though, scientists could not see the object itself. It surprised them because if it was a star, it ought to emit visible light as well as X-ray radiation. Scientists called this object Cygnus X1. In 1970, as telescopes advanced, they noticed that whatever Cygnus X1 was, it had formed a binary orbit with a star in its system, and this helped scientists calculate its mass. They discovered that this invisible object was 15 times more massive than the Sun. As the densest neutron star had an upper limit of 3 times the mass of the Sun, scientists realized that this was most likely the first ever discovered black hole. Since then, we have discovered many black holes. Massive ones seem to exist at the center of galaxies, and we've even managed to take photos of some, dark blots against a swirling ring of matter that surround them and fall into them, their accretion disk. This is how black holes can still be detected through X-rays. While black holes can't emit visible electromagnetic radiation themselves, the X-rays that come from them actually originate from their accretion disks, where infalling matter gets heated to millions of degrees Celsius through intense friction. Black holes with no infalling matter are basically invisible, with no bright accretion disk to spot. Exploring black holes is still a developing field in physics, and there is still much to learn. From what we have learned so far, you may wonder if a black hole could ever stop being a black hole, or will it grow forever until there is no matter or radiation left in the universe? It would seem so. However, in 1974, in his paper entitled Black Hole Explosions, physicist Stephen Hawking postulated that there was actually a way that energy, and thus mass, could leave a black hole. But to understand why, we have to get into some extremely weird theory. We need to examine some principles of quantum mechanics. But first, let me ask you a difficult question. What is nothing? Imagine for a second a patch of space with nothing inside of it. It has no atoms of space dust, not even radiation passing through it. As near as can be seen, nothing exists within it. And yet, is there really, truly nothing there? Something fundamental exists here, and we can tell that this is the case when a beam of light travels through it. If you are familiar with the properties of light, you will know that light is actually waves of electrical and magnetic charge that are constantly propagating with each other forwards in a straight line. However, let's take a look at that word wave. A wave in the sea is the propagation of energy moving through the water. If you were to look at an individual particle of water, it's not really going anywhere except in a circle. And yet, because it passes energy to the atoms next to it, energy travels towards the shore in a constant motion that goes all the way to the beach. Similarly, a sound wave moves by passing energy between air particles, with each particle only moving a tiny bit, becoming energized and then passing that energy to the next particle in line. But in our vacuum of space, where there is nothing in it, where our photon of light is traveling in waves, have you ever stopped to wonder what exactly is waving? This hints at a fundamental something that exists even in nothing, a fabric that makes up all of reality itself. Quantum physicists call this something a quantum field. Quantum fields are tough to wrap your head around, but they are inescapably important when it comes to understanding the fate of a black hole. So how do quantum fields and exploding black holes tie together? Going back to Hawking's paper, Hawking hypothesized that black holes would release energy slowly over time in initially tiny quantities. As energy and mass were two expressions of the same thing according to Einstein's famous E=mc² equation, this inevitably resulted in a reduction in the black hole's mass. However, as the black hole shrinks, the rate of energy release would speed up, getting faster and faster, until in the very last moments of the black hole's life, it would release a burst of energy that was truly gargantuan in its scale, before vanishing entirely. But how can this be true? It is well known that an event horizon is inescapable, so how could radiation ever leave it and eventually cause such a black hole explosion? The answer is a strange one and relies on unintuitive ideas of quantum theory that completely go against our day-to-day experience. But if it's true, I hope you're prepared for the universe to be a whole lot stranger than you first thought. But to begin understanding Hawking's theory, we need to understand the idea of quantum fields. Remember, light moves like a wave through even a completely empty patch of space, which reveals that there must be something existing even in the nothing, or else light wouldn't be able to wave it. Scientists call this fundamental fabric of reality a quantum field. In fact, they believe that there are several quantum fields, all overlapping each other, and all covering every single patch of the universe, be it past, present, or future. Quantum field defines a particular type of something. One field might define all of the electrons in existence, while another may define quarks that make up an atom. Where nothing can be found, the quantum field is relatively quiet. Think of it like a guitar string that hasn't been strummed, or a graph that has a zero value. But wherever in time and space mass or energy can be found, the quantum field is resonating at that point. And when the resonance reaches a certain threshold or quantity, the universe expresses that as, say, an electron or a photon. It's important to note that in this theory, the resonance is not just reacting to a piece of matter, it is the matter. An electron is nothing more than a resonating section of the quantum field that defines electrons. This is true for all energy and all matter too. According to Einstein, energy and matter are two sides of the same coin after all. All the universe you see around you is resonating quantum fields and nothing more. In this way, the theory portrays all of the universe as a song being played on these fields, which I think is quite a beautiful image if nothing else. But why does this matter? Why is it important to define the universe in this way? Well, due to an idea of quantum physics called Heisenberg's uncertainty principle, sometimes the strings of the universe start strumming themselves. Without going too deeply into this aspect of quantum physics, essentially when we're looking at really tiny objects on the atomic scale, it becomes impossible to know too much about them. You cannot know both the location and the direction of travel of an electron, for instance. Because it is so small, as soon as you try to figure out the location of an electron, it bounces off whatever you are trying to use to measure it, so you can no longer be sure of its direction of travel. If you know its direction, according to this principle, you can't know its location. This is not just because our methods of measuring aren't good enough, but because of some fundamental laws about the nature of the universe itself. According to Heisenberg's uncertainty principle, you cannot know everything about particles on a subatomic level. But when you apply this principle to quantum fields, it gets weird. Quantum fields fluctuate everywhere, and by Heisenberg's uncertainty principle, particle and antiparticle pairs can actually pop in and out of existence.
The how and why get complicated, but basically the universe allows it as long as they only exist for a very short period of time, as ruled by uncertainty relations. You might think this can't possibly be a thing. Matter does not just pop into existence. We would have surely noticed this by now. However, in an experiment done by Hendrik Casimir, evidence was found that suggests that this might actually happen. Casimir took 2 plates of conductive metal and placed them close enough together so that only certain sizes of smaller virtual particles could pop into existence between them. This limited the number of such particles that could pop into existence. But because all types of particles could pop into existence on the outside of the plates, this meant that there was a difference in pressure exerted on the 2 sides of each plate. Theoretically, the larger pressure by the number of virtual particles on the outside of the plate should push the 2 plates together, and in the test, this proved to be the case. You might think that particles appearing out of nowhere seems to defy the laws of conservation of matter. You would be right. So, to balance the scales, whenever a virtual particle appears, a second particle also pops into existence to pair up with the first particle. But while one of the particles is matter, the other is antimatter. A 1 and a -1 on our bar chart, thus keeping things overall at 0. The universe is happy. And on top of that, these fluctuations in the quantum field quickly crash into each other and annihilate each other, removing them both from existence again, so we don't normally have to worry about them. As a side note, there is a theory that antimatter is simply matter that is moving in the opposite direction through time, but that's a level of weirdness that we don't need to get into here. The important part is that the quantum fields are constantly resonating and constantly cancelling each other out. This is why, for the most part, empty space is empty. However, what would happen if you stopped only some of those fields resonating? And that's where black holes come in. Black holes act a bit like putting your thumb on the guitar string of the universe. Due to their event horizons, certain resonances in the quantum fields are dampened down while others are not. Hawking imagines sketching a line through time in a patch of space where a black hole was born. He imagined a quantum field that resonated along this line, stretching from before the existence of the black hole into the future after it. Before the birth of a black hole, all is normal. Quantum fields are all resonating freely and can cancel each other out. However, the emergence of the black hole's event horizon changed the curvature of space, and outside it, Hawking realized that certain pulses were now missing their opposite numbers. As he looked at the math, he realized not everything was being cancelled out anymore after the black hole had formed. Indeed, outside the event horizon, traveling away from the black hole, he found resonances that perfectly matched the shape of thermal radiation flying away into space. Radiation is energy, and energy cannot form from nothing. As the black hole was creating this radiation, the black hole would have to pay the price. Every piece of Hawking radiation would thus coincide with an equal amount of energy lost from the black hole, which in time would reduce it down to nothing. If it exists, Hawking radiation is kind of like money spontaneously appearing outside of a bank, while inside the bank, the money in the vault vanishes. It's also extremely difficult to prove, as Hawking predicted this radiation would be colder than the background cosmic radiation that fills the universe, and would have a wavelength as long as the black hole's event horizon itself. As some black holes have event horizons the size of solar systems, we have no way of detecting this kind of radiation. We'd only really see it once the universe had gone cold and dead, so there was nothing else to get in the way, which would probably mean we weren't around anymore to do the detecting. However, in spite of the objections to it, the math behind Hawking radiation seems to be sound, and scientists have recently taken steps to proving it in the lab. In the Technion Israel Institute of Technology, researchers looking into Hawking radiation came up with an idea to get around the difficulty of measuring a real-life black hole. They did this by creating an analog, a sonic black hole, which would mimic the properties of a real one. They relied on the fact that sound moves much slower than light, so it's much easier to create a medium that moves faster than sound. When it moves, any sound waves traveling in the same direction as it can never quite escape it. Interestingly, Hawking's math worked for these sonic black holes just as well as it did for gravity-based ones, and so Hawking radiation ought to be detected from it. After repeating the experiment 97,000 times over 124 days of continuous experimentation, the researchers detected multiple instances of Hawking radiation and saw that it matched Hawking's predictions of how his radiation might behave. Although this does not prove that Hawking radiation is definitely real for actual black holes too, the fact that Hawking's math worked for this sonic analog is a strong implication that he might be onto something. Hawking radiation might just be real. So, if you fell into a black hole, could you ever escape? Probably not. However, if you waited until almost the end of the universe, the black hole may just radiate Hawking radiation until the mass and energy that made up your existence was completely removed from inside the event horizon. Does that count as escaping? That's probably not so appealing to you. Probably best just not to go in. And that's not the only weird thing about black holes. Their existence implies something quite worrying about our own reality. When you're walking on a beach and you make a footprint in the sand, there is no question in your mind that it is your foot that caused the footprint. The order of causality is quite clear here, so much so that it seems laughable to even need to assert it. You made the footprint didn't make you. But what if it did? What if I told you that on the cosmological scale, the fundamental relationship between foot and footprint might be a little more blurred than you would intuitively think? And shockingly, due to the nature of black holes and Hawking radiation, there is some evidence that this might just be the case. But to begin with, we're going to need to look at a principle called relativity. But no, not that relativity, Galilean relativity. First described by Galileo Galilei in 1632, the idea of this form of relativity is that there is no difference between being completely still and moving at continuous speed. Imagine there are two rooms, one on a ship and another on land. Both are soundproof and have no windows. Imagine the sea is calm, so there's no rocking at all. The only difference between the two rooms is that one is moving and the other is not. Can you tell the difference between the two from the inside? You might think that you'd be able to sense movement, but this is not the case. For instance, right now, you are careening through space at 110,000 kilometers per hour due to the Earth's movement around the Sun. And if you are sitting down at home while watching it, it's likely you would have said you weren't moving at all. In fact, Galileo realized that there was no test that could be done to tell the difference between the two scenarios. He even found that if you dropped a ball in the ship, from your perspective it would look like it fell straight down, even if from the perspective of a person on land it would look like it was falling diagonally. Galileo realized that if you remove all frames of reference, say by being in space, there is no way of telling if a planet is moving towards you or you are moving towards a planet. According to relativity, both are equally valid interpretations. You might have noticed this yourself if you ever looked out of the window on a train just as another train suddenly passed by, quickly overtaking you. Although both trains are going forwards, the other train is going faster than yours, and because you no longer have a frame of reference to compare your motion to, it might look as if you are suddenly going backwards. Einstein took this idea further with his equivalence principle. Here he took the idea of two rooms again, but this time he was making an observation about gravity. If you were inside a windowless room floating in the vacuum of space, and someone started accelerating your room in the up direction, say by strapping a rocket to the bottom of it, if the rocket accelerated at just the right speed, then it would feel identical to if you were standing in a room on the surface of Earth. In other words, there is no way to tell the difference between the acceleration caused by gravity and the acceleration caused by a rocket, assuming you couldn't stop the rocket shaking you with all its rumbling, of course. Both these principles rely on the idea of inertia, that objects do not like to move if simply left on their own, and do not like to stop moving once they have started. Anytime you want a mass to do something different to what it is doing,
a new force must be applied, otherwise it will remain inert. But why would it feel to the man in the room with the rocket as if he were under the effects of gravity? Or perhaps a better question, why would it feel to us on Earth as if we were being accelerated upwards by the effects of a rocket? The Earth is not expanding in all directions at once, pushing us with it, surely. While this is true, Einstein realized that the two felt similar because they both were the same thing, a form of acceleration. However, there is another form of acceleration that better explains how gravity works than simply applying a force to an object to push it like a rocket does. Consider this spinning fairground ride. If you have ever been on such a ride, you will know the power of changing direction as a form of acceleration. When you stand against the wall of the ride, once it gets up to speed, you feel a constant force pressing you against the wall, even when the ride spins at a constant speed. This is because your mass is trying to move in a straight line at each point in the ride, but the curvature of the ride is forcing you to alter your direction. The battle between your inertia trying not to change what you're doing and the wall trying to alter your direction of travel manifest as the force you feel. And as far as acceleration is concerned, there's not much difference between the Earth beneath you accelerating you up and you trying to accelerate down. Einstein realized that this form of acceleration caused by a curving path, was the best explanation for gravity. He came up with a theory that matter and energy cause a warping in the space around it, kind of like how a ball might bend the surface of a taut rubber sheet it was placed on. The larger the mass, the greater the curvature. And once space was curved, any object trying to travel through it would be deflected by that curve. In the words of physicist John Wheeler, space tells matter how to move. Matter tells space how to curve. For small masses, this curve in space would be very slight, but in dense masses, this curvature could get so great that it would be impossible for an object that got too close to it to escape it. These are the conditions we find near a black hole with its event horizon. So, going back to our very first analogy of the footprint and the foot. If a black hole is the foot, the curvature of space around it is the footprint. It's interesting to see all of this in action and to understand how Einstein came to conclusions which would have been almost universally validated by scientists even 100 years on. But there's nothing particularly weird about any of this so far. Understanding the exact mechanisms behind it doesn't make it any stranger. The black hole tells space how to curve, and once curved, any object moving near it is told how to move. Nothing here is outside our expectations based on day-to-day observations. But when we start to look at Hawking radiation, something very strange happens. The most important thing to bear in mind about it for the purposes of our current video is that it is non-local. This means that it does not appear from the black hole itself, but appears from the area of space around it. To be clear, I do not mean beyond the singularity of the black hole, but still within the black sphere. That's hard to define anyway, space as we know it doesn't exist there. Remember, the black ball you see here is simply the demarcation point between inescapable curvature and escapable curvature, the event horizon. I do not even mean right up against the event horizon, although that is sometimes how this theory is portrayed. People sometimes speak of two particles popping into existence right up against the event horizon, with the antimatter particle just inside it so it falls in, while the normal particle is just outside and so escapes. This is not what is happening. Instead, the region of space this radiation can pop into existence is several times the size of the event horizon, a distance up to billions of kilometers away. And when the largest black holes we have can comfortably fit multiple solar systems side by side inside of their event horizon, the idea that a photon of radiation can pop into existence this distance again outside the event horizon is crazy. It happens even in a place where there is literally nothing there. So in short, it is not so much that Hawking radiation is coming from the black hole directly. Instead, it is coming into existence from the curvature of space that the black hole is creating, and can happen quite far away from the black hole itself. But if that is true, then things work completely opposite to what we might expect, as you will see in a moment. Consider what happens in this order. As energy leaves the curvature of space, the curvature lessens because of something known as the conservation of energy. And as this reduction of curvature happens, the black hole then shrinks. This is crazy. This is like the footprint getting smaller, and so the foot shrinks accordingly. It feels very wrong. Things can't possibly work that way. And yet Einstein hinted that such a thing might indeed be possible. In one of his equations, he stated that the curvature of space-time was proportional to the mass energy of an object. But proportional is not causational. There's no presupposition that one causes the other in this relationship. We are comfortable with the idea of changing mass and so changing curvature, but it works just as well if you go the other way and change the curvature to change the mass. If this is true, then it hints at a universe where mass is simply a projection caused by space curvature. When you shine a light at an object, say your hand, and it makes a shadow on the wall, the shadow is a projection caused by the existence of your hand interacting with the light. Normally in this analogy, you might be forgiven for believing that we are the hand. It is our mass that creates the curvature of space around us. And yet, do we really know that it doesn't work the other way around? Are we simply projections, shadows on the wall of the universe being brought into life by something more fundamental going on in the curvature of space-time? And yet, we're going around thinking that we're the thing that's real. We don't really know. Given that all you know is the reality you experience, it would be difficult for you to be able to tell the difference between the two scenarios. But if relativity has taught us anything, it's that if there's no way of telling the difference between the two situations, then we can't completely dismiss that we're in one and not the other. Either that, or the two might be more linked than we thought. Of course, obviously, this is all just a theory. There is no hard proof that Hawking radiation is even a real thing, although there have been some experiments that hint that it might be. But this is just something interesting to think about. And even if it does prove to be the case that reality is a projection, it's not going to affect your day very much. You will still think and feel, and that's more than enough reason for you to go about doing what you're currently doing. But it is an example of how, when we start to examine the very fundamental building blocks of reality by exploring the weird warping effects of black holes, it can cause us to challenge assumptions about our very nature. After all, when you're asking the question, "Am I real?" and the answer is, "It's not certain," that's more than a little concerning. Either way, black holes affect our reality and they affect our universe. And not just because they suck everything within their reach into them and give nothing back. They are the end, the final destruction of the universe, and yet, what if I said to you that they might actually prove to be our salvation? Black holes might provide the answer to traveling faster than the speed of light and solving the energy crisis in ways we couldn't have even imagined until recently. And, as by now I have come to expect, they do so by messing with the fabric of reality itself, and by completely countering my expectations of physics. Perhaps we have been thinking about black holes all wrong. But to understand how a black hole ignores the usual limitations on faster than light travel, and does so in a way that you can benefit from it without having to go inside a black hole's event horizon, and how it produces near limitless energy at the same time, then we are going to have to understand more about the features of black holes than we've covered so far. It's actually quite difficult to say much about a black hole's features at all. Precisely because of the event horizon, we cannot see what the inside of a black hole looks like. In fact, there are only 3 things we can say about black holes with any degree of certainty. They have mass, they have charge, and they have angular momentum. You might wonder how we know these things about black holes, given that no light can leave them to tell us about them. The key to these 3 characteristics is that all 3 of them represent aspects of the black hole that can be felt outside the black hole's event horizon. Charge, for instance, works the same way around a black hole as it does around any other charged object. That is to say, If a black hole is charged, then it will attract objects that have different charge to it and repel objects that share its charge. Think of it like a giant magnet, pushing and pulling on the universe around it. Scientists can track objects that approach a black hole, and by seeing how quickly certain objects known to have a charge move towards it, scientists can predict the charge of the black hole itself. Interplaying with this is mass. The mass of a black hole can also be felt outside the sphere of the event horizon. In fact, it is the main creator of the event horizon in the first place. This is because mass creates gravity and does so in a linear fashion in accordance with the same principles you might find in Gauss's law, a theorem about electromagnetism, albeit with a gravitational analog. So, it's possible too to calculate the mass of an object by seeing how far away objects are before they start to accelerate towards it, and how quickly they accelerate. Although obviously, you need to factor in charge at the same time, or your results might get skewed. Finally, angular momentum, or spin. It is possible to detect the spin of a large mass object, and we are going to dive into the how in just a bit. For now, let's just accept it as a given and recognize that black holes are certainly very high mass objects. There are varying sizes of black holes in existence. The smallest, known as micro black holes, have a mass that's comparable to that of our moon, or 7.35 times 10 to the power 22 kilograms. They fit all this into a space that's just 0.2 millimeters in diameter, which is incredible. It really gives you a sense of how dense a black hole can be, something thinner in size than a human hair, packing the mass of the moon. And that's just the smallest ones. Stellar black holes have a mass equal to 10 times our Sun, and have a diameter equal to 60 kilometers. Intermediate black holes are the mass of 1,000 suns, and fit all of that into a diameter of 2,000 kilometers, which is still much smaller than the Earth. It is the largest black holes that really dwarf us, with masses between 100,000 to 10 billion times the mass of the Sun, and sizes ranging from 0.001 to 400 astronomical units, an astronomical unit being the distance from the Earth to the Sun. But other than those three features, there are in theory no other differences between them. If you put two black holes in the same room and made sure they had the same mass, charge and spin, it would be impossible to tell them apart. However, these three features are enough to have some interesting effects on the area of space outside a black hole. Traveling inside a black hole is impossible. Space and time break down past the event horizon, but we think we know a few things that must exist inside one. Beating in the heart of a black hole, there is thought to lie the singularity. In truth, this actually is the black hole. When we were discussing diameters earlier, that is just the diameter of the event horizon. Again, we are not certain what a black hole actually looks like because light can never escape it. In a space that is infinitely small, there is a point where all the mass of the black hole is packed, so that it is infinitely dense. For the simplest models of black holes, the ones that do not spin, this is a single point. In a rotating black hole, this is more like a little spinning ring, otherwise it would be difficult to define spin for a point that has no volume. Our current physics get very strange around such a black hole. If ideal paths are travelled around this point, it becomes mathematically possible to do some very strange things, like meet up with your own past. This has some disturbing implications for causality and gets into time travel paradoxes like the grandfather paradox. So that probably only shows for certain that our ideas about singularities are not quite right yet. Because the singularity is so small, it'll take the successful merging of quantum theory and general relativity theory to properly explain what is going on inside a black hole, and we have not yet managed to do this. It may one day turn out that singularities do not exist in the hearts of black holes at all, but this is the extent of our knowledge so far. Well, whatever it is that lies inside a black hole, it powers our faster-than-light engine, because like most objects in the universe, it spins. And oh, does it spin! As we travel out from the center of the black hole, we pass through the event horizon with little fanfare. The event horizon actually cannot be detected locally, although a person outside the black hole might watch you slow down to a complete stop as you travel through it. From your perspective, it actually might seem like time is flowing normally. Normally, that is, until the universe outside the black hole runs its course in an instant, because time outside the black hole is traveling so fast compared to you. This is the essence of relativity. In fact, the only evidence you might have that you've passed the event horizon at all is because of something that exists just outside it, the Photon Sphere. In a zone just outside the event horizon, there exists a point in space where if a photon enters it at just the right angle, it will enter a perfect orbit around the black hole in much the same way the moon perfectly orbits the Earth. This infinitesimally thin zone is known as the Photon Sphere, and given the number of photons that have flown past black holes in all the millions of years they have existed, it is probably filled with photons. It is quite possible that you would be instantly fried as you pass through this point. However, it is just outside here that we find the zone that interests us, the Ergosphere. This is the zone around a black hole where we can most easily detect its spin, and this is because, in this zone, it is impossible for us not to move. You see, mass affects space. We see this in the curving effect of gravity on the travel of objects through that region of space. However, it might be more accurate to say that mass drags on the space around it. As it moves through space, it brings a little bit of that space along with it for the ride. And when an object as massive as a black hole spins, there is an effect known as frame dragging. To put it simply, reality around the black hole begins to spin in a whirlpool that cannot be fought against. Much like a real whirlpool, anything caught within the Ergosphere is spun around the black hole, because the frame of reference it sits in is being pulled. Sort of like how a person moves because they are standing on a moving walkway. The greater the spin of the massive object, the faster this happens. And in the Ergosphere, this can occur at a speed so fast that by the event horizon, space is moving faster than the speed of light. You would need to travel faster than the speed of light in the opposite direction just to stay at a relative standstill from the point of view of the outside observer, which of course you cannot do. But isn't this against the laws of physics? Doesn't Einstein say that nothing can travel faster than the speed of light? The answer to that is yes, but black holes have found an interesting loophole. You see, this rule only applies locally. Right where you are, in your frame of reference, nothing can go faster than the speed of light. But thanks to relativity, it is possible for frames of reference to move away from each other so fast that objects in them appear to be breaking this light barrier from your point of view. But if you move next to them and enter their frame of reference, they would seem to slow down and would start obeying the laws of physics again. It's a really weird effect, but frame dragging is an actual thing. It is by measuring frame dragging that scientists can learn the spin of a black hole. However, according to a man called Roger Penrose, there may even be a way of exploiting it. If you were to send a rocket into this section of the Ergosphere, the rocket would speed up due to being caught in the whirlpool of reality. Once it had gained enough speed, it could then fire a propellant in such a direction that it pushed itself out of the whirlpool again, but now traveling at a much faster speed. This method, named the Penrose process, could hypothetically net you energy equal to about 20% of the mass of your rocket. Now, that might not sound like much, but remember, according to Einstein's E equals mc squared, your 20% mass would produce energy equal to itself times by 299,792,458 squared. That's a lot of energy. So to harness this colossal kinetic energy, all you would need to do is travel to the nearest black hole, which is roughly 3,000 light years from us, and enter its Ergosphere with a rocket capable of surviving the intense gravitational forces there. Ideally, you would need to find one that was not surrounded by an accretion disk, because those get up to temperatures of millions of degrees, as they are swung around at near light speeds and melt from solids down to gas and plasma. But you get the idea. Easy. Okay, maybe this is a little impractical for us, but the implications for faster than light travel that black holes demonstrate through frame dragging might just offer us the key to one day beat the light barrier for real. Not by going faster than light ourselves, but by somehow convincing the frame of reference we are in to travel at those faster speeds, just like they do around a black hole. Of course, if this requires the energy of a black hole to accomplish, we might be out of luck for now, but it's an incredible glimpse into what is possible, and scientists are already looking into the power of frame dragging for future travel. But maybe that's a topic for another video. Either way, this all just highlights once again how our universe really is very different from what we might have ever imagined. And here's another surprising thing about black holes you may not have known before. Falling into a black hole is a lot harder than it sounds. You might expect it to be relatively easy. After all, aren't these the ultimate absorbers, quite literally the largest sources of gravity out there? Shouldn't it be easier to fall into them than any other thing in the universe? You might have thought so, but paradoxically, your intuition is wrong. These galactic maws are one of the hardest places in the universe to actually get inside. So much so that during his lifetime, Einstein believed you couldn't get inside them at all. And not only that, but black holes might even eject you away from them at speeds close to the speed of light. Shouldn't it be that these objects would be incredibly easy to get into? Like a slide that gets steeper and steeper the further along it you go, you might expect to speed up more and more the closer you get to the black hole center. However, while this is right, it is also wrong. You do speed up, so much so that your speed will begin to approach the speed of light. However, in almost all circumstances, you will not find yourself approaching the center of the black hole. And this isn't me talking about some strange quirk of time or relativity, but something that will be observable from whatever frame of reference you're watching from. Confused? Don't worry, allow me to explain through the real-world example of something called an accretion disk. Black holes are, at their very heart, very simple. In something known as the no-hair theorem, black holes are said to be devoid of almost any feature, just like a head with, well, nothing on it. The features of a black hole are usually fairly plain too. They have charge, mass, and spin, and that's about it. As such, accretion disks are not actually a necessary part of black holes. Black holes can exist just fine without them, sitting there, dark and unobservable in space. However, when mass, such as an unlucky star, strays too close to the black hole's gravitational pull, it can be torn apart by the vast forces at work and sucked towards the black hole's center. Strangely enough though, this matter does not all immediately fall into the black hole's event horizon. Instead, the matter usually coalesces into a sort of flat ring that orbits around the black hole outside the event horizon. While eventually it does all enter, this process can take a long time. Some accretion disks take 100 to 1000 million years to be completely absorbed. So what is going on here? Why does the matter not simply enter the black hole? The answer is that it comes up against a surprising principle of physics known as the conservation of momentum. First described by mathematician John Wallis in 1670, and then pioneered by his contemporary Newton a decade or so later, the idea goes like this. If you have a group of objects, the motion of those objects, aka their momentum, collectively must always remain the same. If one particle with momentum bumps into a particle that is standing still, and both bounce away from each other, the amount of total motion for the two particles must equal the amount of the first particle on its own. No momentum can be lost. If you have a rocket on a launch pad with zero momentum, it can only give itself momentum by firing a propellant in the opposite direction. Once you add up the amount of momentum imparted to the air by the propellant going down, and the amount of momentum given to the rocket by going up, then the upward momentum and the downward momentum are equal, resulting in the same net zero momentum you had to start with. This falls a little outside our expectations. After all, we as humans often stop and start walking around, seemingly without obeying this law. However, if you evaluate all the particles involved, this law is always kept. You would struggle to move anywhere without a floor to push against. Momentum imparted to the floor must equal the amount of momentum imparted to you, but in the opposite direction. You just don't notice it because the floor is so much bigger than you. The amount of momentum you give to it does not move it in any noticeable way. But what has this got to do with falling into a black hole? Well, consider this next example, this time to do with angular momentum. Imagine a ballerina who has their arms outstretched and is spinning on a single point. The particles in their hands have momentum. They are moving a certain distance in a certain amount of time. However, when they tuck their arms close to their body, what happens? Well, they suddenly start spinning much faster. This is a classic example of momentum trying to be conserved. You see, the momentum in the hands is still trying to travel at the same speed it was previously traveling at. However, suddenly because it's close to the body, it's now traveling a much smaller distance, but is doing so at the same speed. Effectively, it has much less distance to travel to complete one revolution, and as a result, completes that revolution much faster. This causes the ballerina to spin faster when they tuck their hands in, and slower when they stretch their hands out. Now imagine this on a cosmic scale. In most scenarios, matter does not fall in a perfectly straight line towards a black hole. Almost always it will miss it slightly and will start spiraling in towards its center as it's caught in the black hole's gravity. It now has angular momentum. As it gets closer towards the center of the black hole, it starts speeding up, moving at the same speed on a smaller and smaller orbit, gaining more and more angular spin the further down the gravity well it falls, just like the ballerina. You want to go a little further in? You have to spin a little faster. However, unlike the ballerina, this matter has the speed of light to contend with. Nothing in the universe can travel faster than the speed of light. This is a law discovered by Einstein. So what happens to our spinning matter as it falls further and further into the black hole? Due to the massive forces and curvature involved, it eventually reaches a point where it cannot go any faster. It's hit a roadblock. And because it cannot spin faster, it cannot fall further into the black hole. This has several effects. To begin with, as you can imagine, that creates friction. All of this matter, spinning at such blistering speeds around the edge of the event horizon, starts bumping into each other. And when this is taking place at near light speeds, things get very hot. Matter in a black hole's accretion disk can reach temperatures up to 10 million Kelvin. This is enough to melt anything down to a hot plasma. All these constant collisions pummel the atoms involved, causing them to give off more and more of this energy, like squeezing a lemon. This reduces their mass. Between 10 and 40% of an atom's mass is given off this way in the form of energy, which then radiates out across the universe. For point of comparison, nuclear fusion, the process taking place in the Sun, converts only about 0.7% of mass into energy. Let that sink in for a moment. Consider how bright the Sun is at 0.7%. How bright can a black hole's accretion disk get? The brightest such disks are known as quasars, and they can reach brightnesses that exceed 1,000 times the total brightness of every star in the Milky Way combined. The good news is that, additionally, some of that momentum starts to be shed with the departing energy. More gets shed by imparting it to matter further up out of the accretion disk, as faster moving particles knock into slower particles moving just above them, giving them an extra push and slowing down the lower particles. In this way, matter starts to lose its angular momentum and begins to finally fall into the black hole itself. More momentum can be shed through one of the most striking features of quasars and black holes, their jets. We don't understand everything about these jets, how they form and what they are comprised of, and only a small fraction of black holes with accretion disks have them. But current theories suggest that they are caused by magnetic forces that are created by the spinning accretion disk, or even the rotational power of the black hole itself, which draws up material from the accretion disks and fires them out into space. It's likely that as the accretion disk spins, magnetic fields form, in keeping with Ampere's law, due to all those moving electrically charged particles. The power and shape of these fields are such that there is only a narrow channel at the north and south poles of the black hole for particles to escape. These magnetic fields may work in a similar way to the rifling on a gun, channeling particles down a narrow barrel. Particles moving at near relativistic speeds have only one direction they can go, even though we don't quite know yet why they go. Perhaps they are like the steam of a kettle, fired out through the only gap that exists in the face of this incredible gravitational and heat pressure. And when they go, they go. Relativistic jets travel further than the galaxies they originate from, and are often millions, if not billions, of light years long. One jet with this catchy name has its X-rays reaching Earth from 12.7 billion light years away, albeit faintly. This is because the radiation produced by such jets is very focused in one direction. In an effect known as relativistic beaming, or the Lighthouse Effect, when the beam is pointed away from us, it is much harder to see. Take for example the now famous M87 galaxy. Here, very clearly, a relativistic jet is detected by Hubble. This is the one coming towards us. There is very likely another jet, but we can't see it because it's going in the other direction. It's worth noting that this energy does not come from the black hole directly. Remember, nothing can escape from a black hole. Instead, the matter and radiation come from the accretion disk surrounding the black hole. And again, a lot about these jets is still theoretical. We can see them, even observe them moving over time, but we don't fully understand them or what causes them. Our understanding of accretion disks does not even fully explain how conservation of momentum is kept. There is still some mystery about where all the momentum goes, but the sheer power at play is undeniable. Einstein may have been wrong. It evidently is possible to fall into a black hole, but when some black holes are firing material away from them at near relativistic speeds for distances spanning galaxies, well, it's evidently possible to not fall into them too. And once you factor in the force of matter that is millions of degrees hot, pushing out at you as they attempt to shed their own momentum, perhaps you wouldn't want to get too close to one anyway. So, we've seen how the awe-inspiring effects of a black hole can span entire galaxies, but it begs the question, how big can a black hole actually get? Finding the largest black holes is not difficult. All you need to do is look at the center of large galaxies. These supermassive black holes have grown since their formation billions of years ago. More and more matter fall into them, continually increasing their mass. The very largest of these supermassive black holes can be billions of times the mass of our Sun. However, it may come as a surprise to you to realize that some of the most massive black holes we know of are actually the youngest. You see, when we look at distant galaxies, we are also looking back in time, and the galaxies billions of light years away often have the largest black holes. If the universe is only 13.8 billion years old, and light takes billions of years to reach us, that means the galaxy we are observing can only be a few billion years old at most from our perspective. Pretty young for a galaxy. Surely though, it should be the case that nearer and thus older supermassive black holes are more massive, seeing as they've had so much extra time to consume matter falling into them. So what's going on here? The very largest supermassive black hole we know of is known as Ton 618, with an incredible mass of 66 billion solar masses. By itself, its mass is comparable to the Milky Way galaxy. However, Ton 618 is exceptionally far away, and it's taking light emitted by it 10.8 billion years to reach us. meaning we are observing it as it was 10.8 billion years ago. This means it can be at most around 2.8 billion years old. By comparison, our own Milky Way galaxy is approximately 13.6 billion years old. Yet the supermassive black hole found at our galaxy's core, Sagittarius A star, is only 4 million solar masses. The Andromeda galaxy's supermassive black hole, while bigger, is still only 200 million solar masses. One of the big factors to consider here is the difficulty in detecting and measuring black holes. This is still a really new field of research, as technology has only just allowed us to start observing black holes in the last few decades. Even then, we can often only observe the area surrounding black holes, that is, before the Event Horizon Telescope came along. But even that telescope takes ages to image just one black hole, so our general understanding really is still quite limited. In fact, most of the distant black holes we know about can only be seen because they are quasars. TON 618 is a quasar. Matter is pouring into the black hole's accretion disk at an incredible rate, and because of this, it's erupted into a quasar. Quasars can only be sustained as long as matter is falling into them, otherwise they revert back to dark black holes. It's hard to fully grasp the physics of the accretion disk, but it is believed that the friction here is so great, the accretion disk of a quasar by itself can produce thousands of times more light than entire galaxies combined. TON 618 produces as much light as 140 trillion suns, completely outshining the galaxy it resides in to the point that we can't even see it from our perspective. However, because quasars are the brightest objects in the universe, they can be seen from very far away. So, one reason for large black holes being far away is down to something known as Malmquist bias. This is where brighter objects further away appear more plentiful, when in reality we simply can't see the dimmer objects at that distance, implying there may be an argument that the largest supermassive black holes are actually distributed fairly evenly throughout the universe. If a galaxy has a very large black hole but it's not a quasar, it means we won't see it after a certain distance because a galaxy is much dimmer than a quasar. Another reason why we don't see the biggest black holes close to us is due to the nature of the universe itself shortly after the Big Bang. As you may know, the universe is ever expanding, and during the early universe, matter was a lot closer together. Quasars were more common back then because they need extreme amounts of matter falling into them to give off light, and there was a lot more gas around during the early stages of the universe. Not only has the universe expanded, but over time, gas gets converted into stars. Some of the largest types of stars eventually turn into neutron stars and black holes themselves, meaning that they never get recycled back into gas. Less available gas means less gas will fall into a supermassive black hole. One of the theories for the fate of the universe is actually based on this, called the Big Freeze, where after some trillions of years, all the gas in the universe is eventually converted into black holes. Even now, we see some galaxies where their gas has been completely used up, meaning no new stars can form. These are called elliptical galaxies. Spiral galaxies still have gas and dust structures, and thus can still produce new stars. It is interesting that most of the largest supermassive black holes appear to be in elliptical galaxies where there is no gas left. Gas needs to lose momentum to fall into the galaxy's central supermassive black hole, and if that happened, then the supermassive black hole is likely to be much bigger because of all the infalling matter. With elliptical galaxies, this has already happened, whereas with spiral galaxies, this hasn't happened to the same extent. One such trigger for gas losing angular momentum could be the gravitational influence of nearby galaxies, or even collisions with other galaxies. In addition, there is less gas available in the universe now than there was during the early universe, so black hole growth probably occurred rapidly then, but has slowed down now. This might be why there is no quasar within 500 million light years of us. As the universe ages and things become less chaotic and more spread out, the number of active quasars has decreased, which means the only quasars we see, some of which are the largest black holes we know of, are the ones that happened a long time ago. So, Why are the largest supermassive black holes often the youngest? Well, although it may appear that way, it might not actually be the case at all. We can measure distant bright quasars simply because we can see them. Older and closer black holes may also be large, but because of Malmquist bias, we haven't found them yet. As studies continue and technology improves, we'll start to get a more complete picture of the universe around us.
So there we have it, almost everything you could want to know about black holes. Is there more to be discovered about them? Almost certainly. But one thing's for sure, they have completely distorted my concept of what is normal in this universe of ours. If you found value in this video, be sure to subscribe and like, and even share with someone that may enjoy it. Thanks to my patrons and members for your support. If you want to add your name to this list too, check the links in the description below. All the best, and see you next time.